All right, this is 15.3, part two. Part one was just a refresher for some who might need it for polar coordinates in pre-calculus. Okay, so now in this part, before we start integration, I want to go back and answer one of the questions that drove me absolutely insane when I was learning this stuff. Okay, and it's this: when we're going to polar coordinates, okay, and we're doing integrals, there's this stinking R that shows up, and for the life of me, I could not understand why it was R dr d theta, why it wasn't just dr d theta. Because when we go in Cartesian form, it's delta x, delta y goes to we take it from our Riemann sum. It goes into our simple dx dy. And so again, the physics, the applications are in the Riemann sums, and it's maddening when you're first learning polar coordinates and setting up Riemann sums in polar coordinates, why the R shows up. And so I want to try to clear that up a little bit in this video. I'm going to try to give you we're going to wave our hands a little bit, but I'm going to try to give you some justification for why that R needs to be there. So what I want to do is I want to go back to doing something in Cartesian form. Imagine that we're trying to set up a domain in our Cartesian form, and our domain is just this. Maybe it's the set of all x, y, and guys, I'm not going to be clever, such that x is running between 2 and 5, and y is running between 1 and 4. And so if we're thinking about like trying to graph this thing, hopefully everybody's now like, okay, well, here's 2, here's 5, here's 1, here's 4. And what we get is if we look at x equals 2, run that coordinate curve, x equals 5, run that coordinate curve, y equals 1, run that coordinate curve, y equals 4. Like Dr. One, why call them curves again? Well, because that's what they are when we extend the idea. Okay? And then if we look at x running between, give me any x between 2 and 5, y is correspondingly running between 1 and 4. And so this is my domain. My domain ends up being, not surprisingly, that rectangle. Now, if I'm setting up to do a Riemann sum, then maybe I'm gonna chop delta x, chop my 5 to 2. Maybe I'll chop that into 4 pieces just to get something. Then my x sub k's is going to be equal to 2 plus k times delta x. I'm not being real careful, but hopefully you guys are familiar with this now. Maybe delta y will chop into 3 pieces as a first approximation. And my y sub k's are equal to 1. So my y sub j's are equal to 1 plus j times delta y. And so what that does is, if we just take this is x0, this is x1, this is x2, this is x3, this is x4. The coordinate curve, Dr. One, stop it. The coordinate curve x2 goes this way, coordinate curve x1 goes that way. Similarly, we chop this into 3. There's y0, y1, y2, y3. My coordinate curve y1 runs this way, y2 runs that way. And you know that we call this delta x, delta x, delta x. This is delta y, delta y. And then if we just run our coordinate curves, we see that we end up chopping our rectangle, in this case, into 12 pieces, And then typically what we do for our Riemann sum is we just, for everybody in one of these pieces, we typically, if we're doing a right-hand sum, just pick the furthest right and the furthest up corner. Like, for example, this would be, in this case, that point right there would be x3, y2. And in our approximation, we're just going to evaluate that at whatever, it was a space sheet and what we're looking at, f of x3, y2. And then if we were looking for volume underneath it, then we would say, well, how much area is there here? And it's like, well, okay, well, this isn't bad. This is delta x, the distance between here and here. And this is delta y. And so then we would have our delta x times delta y. And again, you can see why we're making videos. The notation would be so miserable to see over Zoom. The notation would be so miserable to see over Zoom. Now, hopefully you watched the last video where we were introducing again something that you learned in pre-calc, which is polar coordinates. Now imagine we're doing the exact same kind of thing, but we're working in polar coordinates. We have a domain that is much more amenable to circles versus rectangles. And so, for example, suppose that my domain, and I'll work up here, my domain in polar coordinates is all r theta, all ordered pairs. Now guys, this is not xy. This is not xy. We're not saying we move over r, you move up theta. No, no, no. You're given an angle. You're given an angle theta in a radius r, and that gets your point in the plane. But I'm thinking about, okay, I've got a domain, and I'm going to and again, I'm not going to be real clever. So imagine that r is running between 1 and 7, and theta is running between let's just say, pi over 6 and pi over 3. Okay, and what we want to do is set up a Riemann sum. We want to set up a Riemann sum just like what we were doing here. And you're like, okay, well, let's do the same kind of thing. Let's chop r, the interval with r, into 4 pieces, and let's chop the interval with theta into 3 pieces. Well, it's the same kind of thing. My delta r would be equal to, it's no different, b minus a, 7 minus 1 over 4. My r sub k's are equal to 1 plus k times delta r. Let's chop theta, the interval for theta, into 3 equal pieces. Well, delta theta would be equal to this angle, pi over 6 radians, minus pi over 3 radians, divided by 3. I'm glad we don't need calculators. I'm glad we're not even going to do this. We're just going to do it visually. And my theta sub k, so these angles, theta sub k, are just equal to the same thing, pi over 6, sorry, j, I need a second variable, plus j times delta theta. Okay, so now let's try to draw what this looks like down in our Cartesian planes. So we're here, and I kind of know we're only going to be using the first quadrant. So we're here. Now, if you watch the video, hopefully you guys could graph what we have. We have r equals 1, but remember, r equals 1. Theta is allowed to do whatever it wants, creates a coordinate circle. So it's going to be a circle of radius 1. R is stuck at 1, theta is allowed to do whatever it wants. And out here's 7, and now I don't know how well I'll be able to draw this circle, but we'll do our best. And so if the radius is always 7, if R is always 7, and theta is allowed to do whatever it wants, then of course it would keep going. It would keep going. I just don't have room to draw it. Now let's think about the coordinate curve. Dr. One, stop it. The coordinate curve, if I'm thinking about theta equals pi over 6, now the angle pi over 6 chops this into 3 pieces. So this would be like the angle pi over 6. And now r is allowed to do whatever it wants, so it's going to go, r is going to do something like that. And then at theta equals pi over 3, and r is allowed to do whatever it wants. And we end up with something like this. And so now, this piece in here, this piece in here, and if you're not seeing that, you better go watch that video. This piece in here is like the domain we're talking about, this slice of cheese. Okay, so now we're chopping our radius into 4 pieces. So if we're thinking about this, this would be like R0, 1, R1, R2, R3, R4, which would be 7. And if we let theta do whatever it wants, this would be like R equals R1, that would be that, R equals R2, and this would be like R equals R3. Now theta we're chopping into 3 pieces, so we're going to have chopping this into 3 pieces. So this would be like theta 0 equals to pi over 6. Up here, 3 pieces, this would be theta 1. Remember, it's equal to pi over 6 plus a delta theta. So my delta theta is actually the angle. The delta theta is actually the angle between here and here. This is delta theta. Now remember, it's an angle, it's not a length. This is delta theta, and this is delta theta. And again, hopefully you're seeing why we're not doing this over Zoom. This is theta 2, and this is theta 3. Okay, now again, if we're doing a Riemann sum approximation, we would always be trying to do, if we're doing like a right-hand sum, if I'm interested in this piece right here, I'm going to choose my highest radius, which would be R3, my bigger angle coordinate, which would be theta 2. So that would be the thing I would use in my approximation. I would use that point, and again, this is kind of like my x3, y2. And so this would be my R is R3, theta is theta 2, and that's the thing I would plug into my function. Now, if we're finding volume, this is the area that we want. Now, notice how much different this is than what we had over here. Irregardless of where I pick my approximating piece in my Riemann sum, in my domain, it has the exact same area. But if I look at this piece here versus that piece there, there's no way that's the same. There's no way that's the same area. Okay, and that's what's forcing the R to be in our approximation R dr d theta. So we're going to ask, well, what is delta R times delta theta, and then where does this come in? Okay, so what I want you to do now is stop the video, because I know you're already wiped out, and I want you to stand up, and we're going to go back in geometry a little bit, okay, and that's going to help us. I'm going to erase all of this, leave that. I'm going to erase all of this, leave that, and then we're going to try to understand about delta R, delta theta. But go get yourself some water, go take a little break, because you can't ask questions. And I'm going to erase all of this. You can pause the video. This is not exciting. And clearly, it looks like I have to clean the board. All right, I know this is not exciting. Hopefully you've already moved ahead to where you've stopped seeing me be the janitor and mopping up the board here. Okay. All right, let's go back to geometry. Like Dr. Warren, I never really liked that class. Let's go back to geometry and imagine that we've got a circle. Remember, with a circle, we've got a center and we got a radius. And let's imagine that we've got some angle theta between two radii, And we know the angle theta. Okay, we know the angle theta, and suppose that we know the radius, r. So like, for example, suppose theta is pi over 4, and the radius is 7. Should you be able, given that piece of information, to find the length of that arc A? So what's the distance? Not what's the angle's theta. Okay, regardless of where I'm at on that circle, the angle's theta. But what's the distance A? If you knew that this was 7 and this was pi over 4, should that be enough information to determine the length of that arc? And the answer is yes, but the question is how? So go ahead, ask me. Say, Dr. Warren, how do I find that? And I'm believing that was nobody else was paying attention in the Zoom. Everybody else wasn't focused. But then Kelly's like, Dr. Warren, I'll humor you. How? So she pushed down the space bar and said how. So Kelly, I'm glad you asked. So I'm looking at this, and how do I find this? Well, we're going to use some of the things that the classic Greeks gave us, which was proportions. It's amazing how much of what's difficult, seems difficult, goes back to either similar triangles or things related with proportions. So if I look at my radians and I look at theta, theta is a chunk of the circle. If I'm thinking theta radians is part of this circle, but if I think about going all the way around in radians, all the way around the circle, it's 2 pi radians. So if I look at theta over 2 pi, my angular measure over the angular measure all the way around in radians of the entire circle, 2 pi, the Greeks told us that's going to be proportional to this arc over the distance all the way around the circle. This part versus the distance all the way around the circle. Now, you should know how to find the distance all the way around the circle. If I give you a radius like 7, you should be able to tell me how far it is around the circle. So what's the formula for the circumference of the circle? And what did you say? Nothing? Well, now how about answering again? And okay, now I think I hear Trinity. Oh, 2 pi r, 2 pi r. Okay, so yes, if I think about this would be proportional to the arc's length divided by the distance all the way around, the circumference of the circle. And with that, we're able to get a simple algebraic expression to solve for the length of the arc. And we see that the 2 pi's are going to kill themselves algebraically, or that the length of that arc is just equal to the angular measurement times the radius. The length of the arc is just equal to the angular measurement times the radius. So like, for example, if this was 7 and this was pi over 4, then with a good calculator, you'd be able to figure out that that would be 7 times pi over 4 would be the length of that arc. So the length of an arc is equal to the angular measure here times the radius. Now I want to come here, and I want to look at this shape that I've got right here. I want to look at that shape that I've got right here. This is delta r, that we know. This is delta r. This we know. But if I pull this shape out, so imagine that I just pop it out and redraw it up here. I've got a shape that looks something like this. Now I know the distance between there and there is delta r. So this is delta r. This is delta r. Okay, I know the angular measurement. I know the angular measurement here, if I just kind of like extend this down, my angular measurement here is delta theta. And it's an angle, so this is delta theta. This radius is R2. That radius is R3. Now, what would represent the length of that arc and what would represent the length of that arc? So you guys help me out. What would represent the length of that arc and what would represent the length of that arc? And you're like, well, Dr. Warren, it's really good that you derived that identity from the classic Greeks. All I need to know is the angle, theta, and the radius. And so we see, okay, for this one, the radius is R2 and the angle is delta theta. But for this one, well, the angle's still delta theta, but the radius is now R3. And so if I look at this, the length of this arc here would be theta, which is in this case, cleverly delta theta, times R3, and the length of this is delta theta times R2. And hopefully you're following. If not, you're sleeping, but you're going to follow at some point in time. I'm firmly believing. Now the question is, what's the area, or what's an approximation for the area? Because it's just a Riemann sum. We can just use an approximation. And this is where we're going to wave our hands a little bit. This is where we're going to wave our hands a little bit. Ultimately, we're going to let what we were calling n and m, ultimately we're going to let n and m go to infinity. So delta r is going to end up getting really small, and delta theta is going to end up getting really small. But if I think about this, if this is getting really small, if I'm thinking about my delta r, imagine that I'm in a place where delta r is really small. Here's maybe, again, forgive me, I'll call it R2 and R3, just keeping it the same. But now delta r is really small. This is delta r. In fact, on any radii, we're always going to be delta r apart here. Remember, the length of this is delta theta times R3, and this is delta theta times R2. Now this is where we're going to wave our hands. Imagine that I take this, now you're not going to want to do this, but imagine that I take this annulus and I straighten it out into something where I make this flat and this flat. They're always delta r apart. The distance between these are always delta r apart, but if I do that, I get something that looks roughly like this. They're always delta r apart. Now you're not going to like this. If curves become straight lines, then these straight lines here on the end are going to become curves. It doesn't really matter. Now this distance here is delta theta r2, and this distance here is delta theta r3. Now the distance between these is going to get smaller and smaller. The distance between these are going to get smaller and smaller the more delta r shrinks. So like, for example, we can even figure out how much more is up here than what's there. How much longer is this than this? And we can even see what we say, okay, well, let's just do that. It's this length of that arc minus the length of this arc. And you're like, Dr. Warren, algebraically, you can pull out that delta theta, and you're just left with R3 minus R2. But the distance between R2 and R3 is just delta R. So we see that the distance between each of these is a delta theta delta R. The distance between these is a delta theta delta R. And if I'm thinking about the area that we have here of the stuff left over, if I'm thinking about what's left over there, it's going to be, well, the distance is delta theta. It's going to be less than, if I'm looking at what's left over there, it's going to be less than delta theta delta R. That's the distance left there, times this width, which is delta R. So it's going to be less than a delta theta delta R squared. It's going to be less than a delta theta delta R squared. And so as delta R goes to 0, we can argue that this stuff left over will in fact go to 0. Let me just try to motivate that for you here in a second. But before I do that, I just want to write down our approximation. Instead of using, we're going to ignore this. Instead of using, let's just use, put this back in here. If we just use this rectangle, the area of this rectangle as an approximation, it's going to be a little bit more. It's going to be a little bit more than what we actually have in our annulus there, but it's going to be less than what's here. And we're going to argue that in a Riemann sum, this goes to 0 in just a minute. But if I think about what this would be, okay, this is a rectangle. Its width is delta R. We're taking the longer side, delta theta R3. And so length times width. The area that we could use for our approximation here is R3, delta theta, the length, times the width, times delta R. So we can use this as our approximation to our area. And we know that it's a little bit too big, but it's roughly like this. It's roughly like this. And what I want to argue, that anytime you run into a Riemann sum where you have like a delta x squared, I want to argue that in fact, as it turns into an integral, you can argue that anything that's a higher order than delta x squared, delta x cubed, delta x to the fourth, this is a wonderful trick for physicists and engineers. Anything that's higher order in delta x, we can argue that as you take it to an integral, it'll go to a 0. And I want to justify that for you right now. But chances are what you need right now is get some more water. Okay, so you better pause, and then we'll come back to setting up again y the r, even though we're really close to y the r. Okay, so pause, get a drink of water. I'll do the same thing, and then we'll come back and. All right. So let's just imagine for a second. You guys can go back and look at this. Let's just imagine for something. Let's just go back to Calc 1. Imagine you have something that looks like this. You've got a Riemann sum that's got f of x sub k. Forget double sums. But it's just delta x squared instead of delta x. And what I want to argue is that we can argue that if this is an integrable function, then in fact, when you take the limit, this is going to go to 0. Where my delta x is of course equal to b minus a over n, and our x sub k's in our Riemann sums is a plus k times delta x. We've been talking about this. Okay, well if I look at this, this is the sum of k equals 1 to n. Okay, in the summation, the delta x can be thought of as a constant. So I've got a delta x squared, which is delta x times delta x. So I can view this as pulling one of these guys out of the Riemann sum for each n times f of x of k times delta x. And then if we're thinking about taking it to an integral, we're going to take the limit as n goes to infinity of that mess. But using some properties of limits, this is like the limit as n approaches infinity of delta x times the limit as n approaches infinity of this Riemann sum. But this is set up perfectly to go to an integral. This is perfectly set up. My delta x is b minus a over n. My x of k's are a plus k delta x. And we've been playing with fruit in this. This is going to go to the integral from a to b of f of x. Wherever I see an x of k, I put an x. And where I see a delta x, I put a dx. So this limit goes to that number, but it's going to be multiplied times this limit. And remember, delta x is equal to this fixed number b minus this fixed number a over n. And so as n goes to infinity, this is a fixed constant. This is going to go to a 0, and that's going to drive this entire limit in our Riemann sum to 0. So anytime you have a higher ordered delta, okay, you can argue in the limit that will go, if you've got an integrable function, that will in fact go to 0. And so that's kind of my point here. We're making this approximation. We're using too much. We're using too much area, but in the end, the difference ends up being less than that. And in the Riemann sum, that guy's a delta, like our delta x squared, is going to end up going to 0. So in the wash, it ends up being okay. In the wash, it ends up being okay. Okay, again, I'm not sure we're completely there yet, but let's look at what we have. This is our approximation to the area. So the approximation to the area that we're going to use for this piece, we can just make it R3, and now I'm just going to switch it around, delta R, delta theta. And so now, let's imagine that we're now talking about this piece. Well, clearly the area is more. Clearly the area is more. And let's use that point. We can argue that for this one, our approximation can be, now we're not on R3, but R4 times delta R delta theta. I don't know why I wrote 2. R4, similarly out here, this would be R4 delta R delta theta. This is R4 delta R delta theta. And you guys should be able to write down what would that be. So you take a shot. What would the approximation for that very smallest piece in our Riemann sum, where we just used 4 and 3 subintervals? You guys write down what you think it should be. And I'll wait. And this would be R1 delta R delta theta. Okay, so now imagine that we were setting up a Riemann sum. Well, we're going to want to add up over each of these. We're going to want to add up over each of these. Now again, we're not even talking about a surface yet. We've got a surface over here we're trying to find the volume of. But that's going to be our next video. That's going to be our next video. But essentially, we're going to have a Riemann sum. It's much easier to write it as j goes from 1 to 3. A Riemann sum as k goes from 1 to 4. That's how many pieces we chop that into. We're going to have some function in here, but then we're going to have our areas, which is going to be well, you can see, an R sub k delta r delta theta. And this gives, at least what I hope, is a little bit better justification than what I got, even though we're still waving our hands, of why this r needs to be in our area approximation that we're going to be using when we're trying to integrate over polar coordinates. Okay, so we're just going to stop with that. We're just going to stop with that, but I'm hoping that gives you at least some sense of what's going on.